double check. Okay. So it's on. So actually, it looks good at this end, but I have no idea if there's any echo or any other problems. I hope that I'm using this mic. I hope so. So there's a major delay.
Yeah, it's fine.
It's fine. Good. Good. So let me put this off from here. So let's continue then. So flow types. This is what I pretty much explained to you already. So how is the mathematics in different flow types? So in a laminar flow, it's very important to understand that the relationship is a relationship between the flow rate as a pressure difference is linear relation. And what is the one that connects or relates these two components will be a coefficient that depends on your geometry. This is what I strongly recommend to take a look at the pre-calculated tables. There's a number of different kind of pre-calculated tables available, and using these tables you can define how is a CL. So C, the associated laminar flow. Now, I have here a few examples, and again, I need to apologize that the one, something that is in the left is not clear, so it's very, very, unclear actually. So even, okay, so the first one is, seems to be a hole that is a rectangle in a shape. I don't know how it is that you can manufacture rectangular shape. Well, let me see. Yeah, rectangular shape hole like this. So the dimensions are, I think this is B. So B, this is H. And then the length is how long is this this kind of weird shaped hole. So this is L. And then I have, with this I think it is not very practical and not commonly used in reality. But then I have here drilling. And the drilling is such that the dimension of the drilling is D. And the length is L. So this is L. Take a look at the slides after my lecture. So D is a diameter of the drilling. And now, again, I would like you to pay attention to this. The flow rate and the pressure difference, they are linearly related. So that's the first very important observation. Another equally important observation is that what affects the flow rate here is viscosity. Viscosity is in a plate. So you need to know the number of viscosity, and it's only important in this kind of a laminar flow. Okay? More examples that are even more unclear. Okay, I think this was a, okay, never mind. Take a look at the PDF later of my lecture, and then you will see these examples. But what I would like to explain here is that, using these pre-calculated tables, you can find the relationship between the flow rate and the pressure difference. What's that?
We can see it better like that.
So you can see what?
We can see the
Pictures with this.
Really?
Yeah, with the cross sections.
It's like a cylinder.
Yeah, but.
Good. Very good. Okay. Or you can take a look at them later when I provided the PowerPoints in Model website. Okay, so this is it. Then the turbulent flow. This is something that, again, important to see that how is the relation. So the relation is something that the flow rate and the pressure difference is quadratically related. So what are the components or parameters that I needed here is something that is called discharge coefficient, and then the cross-section area and the density of the fluid is included as well. Now, how we're going to do the modeling in reality will not be the equation as shown here, because this kind of equation will be a little difficult to use in practical applications. We're going to use something that is a little different technique. It will be based on analytical equations, but we're going to introduce a little bit of manipulation to analytical equations such that unknown parameters can be get from manufacturer's catalog, because that's what we really wanted to do. Here, things are a little difficult, defining the discharge coefficient. I guess it is doable, but something simple like cross-section area of the throttle often is very, very difficult to get. in practical cases, in practical valves. So we are not going to use this kind of approaches. But again, what I would like to tell here, that in case of turbulent flow, flow rate and the pressure difference are quadratically related. Okay? Now, throttle valve. So let's take a look at the components. So the direction valve was not the first one that I would like to introduce you, but instead the first component is a throttle valve. So it's a simple valve that introduces the pressure losses. So it's something that if I have a pipeline here, you know, the throttle valve is something like this, and the flow goes through this kind of throttle, and it will introduce the pressure differences. How is that we can model that? That will be introduced in the beginning, just that you can have a clear understanding how is the method we use. And the method we will use will be called semi-empirical approach. Semi-empirical approach, semi comes from the fact that it's a combination of analytical equations and measurements. How we do that trick, that I will explain to you next. Okay, so modeling the valves. So let's make the few general observations first. So valve modeling is typically something that first of all we have to make a model about the spool position. Spool position is like mechanical component, is something that moves in a different location, either because of the pressure forces, spring forces, flow forces, or magnetic forces. But we first supposed to have an idea where this moving component is located at. Once we know that, then we can actually make a simple model that describes the flow rate through the component. If looking the pressure relief valve as an example, you know, we have here, you know, this is the first of all, the drawing symbol for pressure relief valve would be something like this. So there is a hose that is connected here and hose that is connected there, and then I have here is closed in a typical operation condition, and this is a pilot driving that is actually moving this arrow to be here, and once it's here, then the flow goes through. So in reality, I have here a spoon. Spoon is here, and then the pressure that comes through this drilling here is a little bit unclear picture, and I need to even change the color here. So here is a drilling at the throttle here, and the drilling that comes here, and it applies here. It's a little less than the pressure that applies here. But this is the one that makes this spool to move upright direction. And once it moves upright direction, it connects the flow such the way that flow can travel here to here. So that's what the component is about. Now, in order to estimate the flow rate, we're supposed to know, okay, well, how much is the opening? And the only way to know that is by knowing the spool position. We could kind of make a model where we're including all the physics of these moving components. We could create the equation of motion for the spool because that's where we are very good at. So based on the multi-body system dynamics, we could know, okay, this is the equation of motion, and based on the equation of motion, we can estimate the spool position. This is going to be very difficult, and we're not going to follow that. But we're going to cut the corners a little bit, and we will make a simple estimation about the spool position. And once we have a simple estimation about the spool position, then we even go further from that. We go from this, where is it? This one here, this flow equation, and we're going to actually model the flow equation such the way that we're going to have just the flow multiplied by semi-empirical parameter multiplied by pressure difference. This semi-empirical parameter we can obtain from the manufacturer's catalog. So that's the idea. And this one, C, will be a function of spool position and everything else that is actually important for this component. But we can step more details than this. We can step, of course we can, but then the computation will be very heavy and is no longer serving the purpose. Okay? Did you follow me? Seriously? Okay, nice. Very nice. Okay. Okay, so this is what I pretty much explained. So we should first make a model about the moving components, and then we can estimate the flow rate through this component. Now, the different approaches to make this happen, they can be categorized such that we can either use empirical models. And now I need to move this window a little bit to make this more clear to you here. Now, the empirical models are just a set of experiments, set of measurements. And we can create the black box based on these measurements, and the black box will act in such a way that we will send the input signal of the black box that will be the measured signal, and then what comes out is a flow rate. That's theoretically, this is possible, but very much against the idea of virtual engineering, where we want to do everything by using computers, because this approach requires extensive number of measurements. And now we don't want to go and do the measurements, but instead we would like to use, computer simulation as much as possible without stepping into the world of measurements. Okay? Then analytical models, that's pretty much what I explained. So we can take these analytical models and we can create the equations for spool position and flow rate and all other details. And based on that, we can create the simulation model of the hydraulic components. We're not going to go with that either. And why not? Because getting these parameters that are needed in analytical models will be painful, very, very painful. Just to give you an idea, why it is painful, we can go back to this pressure relief valve. Even though that this is a little bit unclear picture, but you can see what I have here in the pressure relief valve. I have this drilling, or this pilot drive here, this one here, which is physically the one that is, okay, I need to change the color again. The one that is this one here. Okay, what I have here in this line is I have a drilling. So it's the drilling that is in the middle of the steel. How is it we can find it out, like what's the diameter of that drilling? Well, of course, hammer is the one that we can use, to break the component to pieces and then finally measure it. Or since, saw and, flywheel and other stuff, we can break it. But we have to break it in order to get these parameters. We don't necessarily need to do that because the properties of this valve is actually measured already. And this information is provided in manufacturer's catalog. So we can simply go in the manufacturer's catalog and take a look how it is. And that gives us an indirect way to measure these parameters. That's exactly what we're going to do. And that's exactly what is called semi-empirical modeling approach. Have you ever met Professor Heikki Handels? You have? Okay, so when Heikki made his doctoral thesis, he was one of the first people that introduced this semi-empirical modeling approach. And his background is in hydraulics. So he is actually the one that is a little bit of kind of behind of this kind of modeling idea. And it's still very extensively used. It makes a lot of sense. It makes a lot of sense. So next time you see Heikki Handels, no, not this, this is for this team only, but this, okay? All right, so let's take a look. Let's look at the example. Okay, so analytical model for throttle valve as shown here. So I have here, the drilling here, which is a diameter, is a round in shape, and the diameter of the drilling is D. So I can compute the area. So it's going to be P multiplied by D power 2 divided by 4. That's going to be the area. Multiplied by discharge coefficient, the one that is coming from the hydraulics. That is then multiplied by square root of 2 divided by density. And then I have here pressure difference. So this is a P, delta P. Okay, that's my analytical model. Now simple component or simple parameter needed in a model is a D here, diameter. Again, not that easy to get because it's somewhere inside of the component, so it's less straightforward to measure the diameter. So what we will do then is that instead of using these parameters, we will replace all the parameters by something that is called semi-empirical parameter. Now the semi-empirical parameter obviously is the one that includes all the unknowns, discharge coefficient and the cross-section area and the density. Okay. Now this one here, this CV, which is a semi-empirical parameter, we can get from the manufacturer's catalog, because the manufacturers, they're providing something that is called characteristic curves, giving information about the characteristics of single component. We simply go to the manufacturer's catalog, we're getting the information, which this time is this CV. We can get it from the manufacturer's catalog, and then we're good to go. Then we have a model. Make sense? No? Yes? Good. Okay. Here's an example. So I have, this is a little bit of theoretical stuff, but next, what I'm introducing the direction valve is, is a material from real manufacturer's catalog. This is what I made by myself. Okay? So I have hypothetic manufacturers, that is Aki's company, and Aki's company is the one that is making the throttle valves, providing the characteristic curves as shown in this picture. Okay, and now in this characteristic curve, I have a curve that relates the pressure difference and the flow rate. The first important thing to look is that, okay, how is this relation? Is it a linear relation or non-linear relation? What?
Non-linear.
Non-linear. Yes, correct. So it's a non-linear relation. So it's a non-linear relation because the linear relation would be obviously this one. But this is non-linear relation. So what is telling us? What kind of flow type we are dealing with? Turbulent. What's up with you today? So you are speaking to me and your answers are correct. Why it is like, what's wrong?
We have prepared.
Yeah, what? That's not allowed. Not allowed here. So that's cheating. Half cheating at least. Okay, so we have, now I got confused because of your responses. I don't know what to say next. Okay, so I'm just going to say this. So we have here, non-linear relation. So what we're going to do then is that we're going to take one point from this curve. Doesn't matter which one. So I'm taking here the one that is corresponding the flow rate 30 liters per minute. By the way, this is typical units used in hydraulics. So it's a liters per minute, or the flow rate or the pressure is a bar. That's not the SI units. Very important to use meters and the SI units in hydraulics. If not, things will go south. I can guarantee you that. And if you want to make a model in your simulation assignment, such even simple modification for this, such that you're using millimeters instead of meters, it will be quite a bit of painful. Possible, but painful. Okay, now we're going to take the value corresponding to the 30 liters per minute. How much is the pressure difference there? That's 100 bars. Now we're going to substitute everything to this equation. This, hold on, this one here, so here. So how it goes such the way that you have first of all solve the CV from the equation. You have here the flow rate in corresponding pressure difference. So the flow rate here is at 30 liters per minute. So to make that in SI units, you have to divide that from 60,000 and then 100 bar. To make that in meters, SI units, you have to multiply that by 10 power 5. And then you're ready to get your semi-empirical parameter. Look at the units. Painful, very painful. So you could change the units, but then you need to be extremely consistent. And this is just the beginning. Rest will be more painful. So just take the meters and you'll be fine. If you want to make your life complicated, then go ahead and use a millimeters, and go ahead and use, I don't know, other units. But it's going to be something that you need to be consistent. And that's what makes that difficult. Okay? Lesson learned. All right? So that was, the final model is this. So I have flow rate here, and then I have the semi-empirical parameter, and then I have something that is called sine. And the sine is a function that provides either 1 or minus 1, depending what's inside of the parenthesis here. So the sine is such that if I have here x, it gives me 1 if this x is bigger than 0. It gives me, I think, at 1 if it is equal than 0, and minus 1 if it is smaller than 0. That's what the sine is about. Why I need to use a sine here? In order to account the fact that the flow can go two directions. It can go back and forth depending where is the highest pressure. Because you're always trying to equalize the pressure difference. So now if this pressure is higher than this, it's going to go this direction, another way around. So it can go two directions. So that's why I'm using the sine function to define the direction. Because I cannot do that using this delta p. Why not? Because the delta p is under the square root, and I wanted to have a positive value under the square root. I don't want to deal with the imaginary numbers. Okay? So the delta p here that is under the square root, I have apps to make sure that is always providing the positive values for them. Okay? Closed. So this is it. So mission accomplished. Any comments or questions? Extremely clear. Okay, extremely clear. I take it that way. Okay, next one, direction valve. So let's take a look at the direction valve. First of all, the direction valve, this is how it typically looked like. So except the digital hydraulics, which I will explain to you perhaps next week. I would like to explain it because that's, I believe that is a little bit about the future of hydraulics. And this is something that can introduce a little bit of energy savings, and it's something that is quite important. But right now, let's look at how is a direction valve. And this is not really the latest model of the direction valve because this is operated by a shaft. I'm sure you have seen these machines where there's a gap in, where there's a lot of long sticks. These sticks are mechanically connected to spool. So they may have a look like this. So you have a stick like this, you take a handle here, handle is here, you're moving this back and forth. Okay, what will happen is when you're moving this back and forth is that the spool position will go in a different location. Now I have here a simple direction valve that is connecting 4 ports, which is a pressure, tank, A, and B. So let me write it here. So this is a pressure, tank, A, and B. Now, if this spool is in center position as it is shown here, then let me take a look. Well, actually, this is not the drawing symbol this in a very good way because, it seems to me that if it's in this particular position, then actually it's supposed to be such that here in the middle position, nothing is connected, right? Corresponding this picture. You agree with me? Okay, when I'm pushing that to this direction, then it's actually connecting pressure and A. So it's this one and this one. And when I'm moving it in this direction, then it's connecting pressure to B. So the pressure to B, A to tank. So that's supposed to be the drawing symbol to my particular direction valve. Now, this is operated by a stick. And that's what this drawing symbol is standing for. Not used anymore. If you see the machine where there's operation by a stick, it may be something that you can find in a truck or something. But then typically how it goes is that there is a gap in where there's a joysticks. And joysticks are electronically connected to direction valves. Meaning that you're using the joystick, the signal goes from your joystick, goes to the direction valve, and there is a magnet that operates spool to go back and forth. This is how it's typically operated. So there is no longer mechanical connection between the handle and the spool position. All right? You agree? Okay? Now, if I have a direction valve like shown here, this is something that I have here. Forget about the flows, but the pressures are such that this is a pressure A. Maybe better to use just A to follow in the previous example. So this is A here, this is pressure here, this is B here, this is tank here. What's going to be the right kind of drawing symbol for the the valve like this? Is it going to be this one, or this one? Not in class quiz, but I'd like you just to know how you feel about this. Let's vote. A. Let's vote. A, B, B, C. Okay, so it's B. This is what it is. Why? Because when it is in this location, the pressure here in the middle location, the pressure is not connected to anywhere. Tank is not connected to anywhere. A is not connected to anywhere, so it's just blocked. This is a typical scenario for the direction valve. This lens of the spool, which is the lens are the ones that are like these ones here. They are just exactly the size of the drilling, so they are just barely able to cover the system such that there is no leakage. In reality, if you have like zero lens shown here, there is always a little bit of leakage, which means that there is always a little bit of flow that can go in this corner here or this corner here, depending on what the pressures. But theoretically, there is no leakage, so it's kind of capable to close everything in a middle connection. But there's a possibility to play with the lens, so it's possible that you can have a lens that is a little shorter than the drillings. So it's meaning that even in a middle position here, all the ports are connected because it's not able to close the ports, but instead there's all the time open. So this is the one that you can carry out by using a slant that is smaller than the drillings, all right? Or you can have exactly same size than the drillings that is shown like here, or then you can have a lens that are bigger than the drillings, and then they are sure that there is no leakage. But this will be a little bit of different behavior comparing, these and these two guys have a different kind of characteristic curves. Okay, this is all clear. Clear? Okay, so this is a characteristic curves that shows the valve opening. This x-axis here is a valve opening. That's the spool position versus the flow at the certain pressure difference. When I have this land shown in a, where was it? In a previous, let me give a words or let me give a titles for this. So let's call this as A, and let's call this as a B. And let's go to the next slide here. I have here this relation, which in the first scenario is a linear relation, and in zero valve opening, the flow is zero. So that's scenario A. Scenario B, you have to move your spool quite a bit in order to introduce even a little bit of flow. So that's the scenario that is shown here. So when the valve opening is, from here to this particular given value, there is no flow. But once you're getting over from that, then the flow is like this. So this curve here is a B. And then there is something that is a proportional curve, which is a linear in such the way that the opening and the flow is a proportional. So it's a more flow getting in, more the opening. And this is typically used in a system where you need the high precision. Because if you want to have a high speed, then you push the pedal as much as you can, and then you can find this scenario where there's a lot of flow going on. But once you're in a certain position and you want to have an accurate position, then you can actually use this progressive curve here in order to have a fine positioning, and it's easier to operate this way. So this is called proportional direction valve, the one that is nonlinear. Okay? So you have, all this stuff, more or less. Okay, what about the valve modeling business then? Now, typically, I don't know, 99%, well, less than that. Most of the cases, the positions valves are electronically controlled. So we have some kind of magnet that introduces into the force to spool in such the way that the spool goes back and forth. So it's a magnetic forces that is moving the spool in different location. And now these magnetic forces are then controlled by joystick or automated system or whatever you want. Okay, we cannot make the accurate models about the spool position if it is a case like that. But we have to do something about it. So because typically this is operated by input signal. And input signal, so the valve is capable to follow the input signal with a certain limitation. So if the input signal is, let me make a drawing such that this is a time, and this is a spool position, and if the input signal is like this, then the spool is capable to follow that with no problem whatsoever. But if we have a step function, say that the input signal is moving from 0 position to, say, full opening like this with a step, then of course because of the inertia and the force is not infinite in a magnitude, the spool cannot follow that, but it's coming with a certain delay. At the certain delay, meaning that is like following like this. But this is simply because of the inertia. The mechanical system cannot jump here to here, as a step function. Not possible because of the inertia and because we don't have infinite forces in our usage. If we have a small masses and a lot of forces, then it's possible to reach this reference position faster than in other cases, but this always comes with a little bit of delay. And this is exactly how we're going to model the spool position. So we're simply going to use a first order differential equation, which is written shown here, as shown here. So I have here first order differential equation where this is an input signal, and then I have here kind of like imaginary spool position, and then I have here something that is called time constant. Time constant tells us how fast the spool can move from one location to another location. And it depends on the quality of the direction valve. So this is the first step. So once we have an understanding about the spool position, then we're ready to make an assumption and description about the flow rate through the component. But very, very, very important to understand that this equation describes spool position, spool position, spool position. Okay, clear? How it happens? Would you like me to repeat it? Or is it clear? You want me to repeat it, or is it so? Yes, no, which one? So it's like you get it.
Yes.
Okay. Yes, repeat it. Or yes, going on.
Going on.
Okay, good. Okay, so this one here, this time constant. How is it we can get that? Well, this is again, this is a real deal. So this is pictures that I took from the manufacturer's catalog. So this time concept we could get from the border diagram. And the border diagram shows how fast is a hydraulics. Not the hydraulics, but the hydraulic direction valve. So there's it's coming from the experiment that I'm sending the signal just to my direction valve, which is a sine function. And I'm just playing with the frequency of this function. And in the very beginning, the frequency is very low, and the spool is capable to follow this signal. But then I started to increase the frequency such that it's becoming like, you got the idea. So I'm increasing the friction. At some point, what happened is that the spool is no longer able to follow this very rapid signal, and it left behind. And when it's left behind certain number, then I can take the number, like they can take this value, I can tell, okay, this is how fast is this one particular valve. And this is coming from the border diagram. So let me show you, I think that I have an example. No, I don't have I'll have an example soon. So this is where this component that is needed in estimation of spool position is needed. So we're gonna take a look at the example. And that's then used in order to estimate the flow rate through the valve. So I have here something that is called semi-empirical parameter telling me how large is a valve. Then I have here spool position and the pressure difference. Those are the three ingredients that I need in order to introduce the flow through this one particular component. Okay. What is this? Spool position, correct. Very good. Okay, physical interpretation of the equation below. So what is that this describe? Is it describing the pressure drop due to the valve, flow through the valve, spool position, number of ports in valve? Okay, so let me see. Next. Okay, and the success rate will go down all the way to 70%. 70, yes. Sure. Okay. So I'm asking a physical interpretation of this equation, this one here. Okay. Okay, what I will do then is that we still have 10 minutes. Well, we have all the night. So we can stay here longer than 4 o'clock. Can we? No, thanks. Next time, perhaps. Okay, so I'm curious. So you done? You all done? You guys done? Okay, let's see what, the online participants are coming, of course, a little later because of the delay. This is like real time what we can see here, but because of the YouTube, it takes like, I think it is like almost like 30 seconds before they can see us.
No, not that much.
Not that much, 20 seconds, 15 seconds.
Yeah, more like that.
Yeah. So now if you make like, if I know that, so if I say something stupid, I have 15 seconds time to close this connection. Well, not like that. Okay. So last time we got like 50 something answers. 51. Okay, 41, I think that may be reasonable because many had enough and they left. No, it's still raising, so the number is getting higher. Okay, 44. Okay, 70. Who say more than 70 or?
85.
85.
90.
80.
90.
90. That's serious number. So you ready? So let me close this in 5, 4, 3, 2, 1. Actually, this counting makes no sense because of the delay. Because it's already, when they hear that, it's already closed. Okay. 82.
Yeah.
82. I say that this is, we're coming down. We came down a little bit, not too seriously. So it's 82. Not bad. Okay. What this is describing, what is the correct answer? That's going to be the C here. Okay. Now what I have then is that I have an example. First of all, this is the equations that you can use in order to create a flow through the valve. So I'm following the idea of throttle valve introduced in a previous example. This time I'm simply going to introduce this, this semi-empirical parameter that is telling me how large or what is the size of this one particular component. Then I have here spool position. Again, I'm using this sine function to make sure that I can describe the flow in two directions. Because in theory, it's possible that the flow is not traveling from the pressure size to A, but the other way around. It's possible. and it is accounted in a similar way than in a throttle valve. This describes the situation when the U, which is a spool position, having the positive position, meaning going this direction. So it's when it's going this direction, it is actually connecting B to A and tank to B. Okay, when it's 0, and I'm assuming that there's no flow whatsoever. When it is negative, then then the A is connected to tank, B is connected to pressure source, and so on. So that's my equations that I needed in order to describe direction valve. Oh, here's the digital hydraulics. This is actually extremely interesting, and I really want to get back to this. And I will get back to this, but not, but it have to be next week. If you have a time, take a look at this. So it's an interesting video about the principle of the digital hydraulics. This is short description. Conventional hydraulics, we have this spool that is moving back and forth. Now, depending on the spool position, we can have either a lot of flow through the component or less flow through the component. We can do the same by using simple Poppet valves that are either closed or open. Fully closed and or fully open. We can actually use these valves in such the way that they are, they are connected together, such the way that the same line, so they're like parallel each other. So if these are the Poppet valves, this is the pressure source is divided to these 4 different places. They can be either closed, open. The digital comes from the fact of, black and white, closed or open. And now you can have these in a different sizes. And now if you open 2 of them, you can have a little bit of flow rate through these settings. If you open all of them, you can have as much flow as possible to do it. And now depending on the different configuration, you can have a small flow or large flow, all because of these Poppet valves. And that's what is called digital hydraulics. Now, it comes with a certain advantages, comes with a certain difficulties, but really the big idea is to use these digital hydraulics all the way in a pumps, because in a pumps, you have to make a decision whether you're producing energy or system or not. And there's ways that you can actually control that. That combined with the digital direction valves, it is possible to introduce some significant energy savings. Okay, we'll get back to this next week, but now let's look at an example. So I have here, screenshots from the manufacturer's catalog. So here the screenshot is about valve opening and the flow rate. The valve opening is something that if you look at the x-axis here is a valve opening. So this is like U, and then the flow is the one that is here in the y-axis. Now the first observation when we make a model of this one particular component is that we have to take a look like how is the relation between the flow and the valve opening. And I can make a conclusion that is more or less linear. It's not exactly linear because if you look at this carefully, when the valve approaches the full opening, there's some linearities, but other than that, it's clearly that linear relation. So I can use this, this equation that was introduced in a previous slide in order to create my semi-empirical model. It mentioned in a manufacturer's catalog that the nominal flow with full opening, that's what it stands for, is 24 liters per minute when the pressure difference is 35 pars. That's exactly the information that I need in order to define this semi-empirical parameter. So I'm going to take this 24 liters per minute, I'm going to put it here, and then I'm going to use this 35 pressure difference. I'm going to put it here. I'm going to convert the units to be SI units, and the fully opening will be standing for the 10, because in a fully opening, here's the value 10. That's where it's coming from. So that's my semi-empirical parameter, and then once moving on, I'm able to define the time constant. This is the one that is called border diagram, and there's something seriously wrong in this border diagram because I cannot see this clearly. Yes. Cannot see it. It's something is cut here. Too bad, because this was a very good story, but the highlight is missing here. And the highlight is this picture, because I cannot show the picture to you. But in this picture, it shows like how is that the valve or the spool is capable to follow the signal where the frequency is increasing all the time. So this too is something that I need to get back to you on Tuesday, next Tuesday. Look at that. So it's 4 o'clock. So how is that we're going to close today's lecture? Should we sing a song and then go back home, or we just close it? A song? Let's just close it and then see you next Tuesday then. So this is it. So this I need to get back to you next week, and then this digital hydraulics I need to get back to you next week. Where is it now? This one. And then once we're done with that, we have a few more components to go. Components that we have to cover are pressure relief, but we are not going to look at the details of that. And then we're going to look at the cylinder and the pump. That's it. That's about the hydraulics. There's one very nice example about the hydraulic modeling. And once we're done with that, then we're going to move on to something else. It is up to you, a little bit up to you. So maybe we can vote before I'm going to close for today. So I really wanted to spend some time about this real-time simulation and games. But what about the flexible multibody dynamics? Are you interested? Good to know. So flexible multibody dynamics, that's what it is. So it's good. Thank you very much. I appreciate that. All right, so let me close. And then see you on Tuesday. You made me feel really good about that flexible model.